Hey everybody, so for today's video, this is a pre-recorded video because webex had some issue saving the video today. So I guess I want to try to at least have a recorded version so you can look back on just in case. So from the Monday's class on the 13th, I ended right about here somewhere where I was doing the initial step for partition and I broke the list into two pieces. So I started off where I had my list where I have L and R, just like that. And I always picked, so I guess the rule of thumb for the assignments when we do quicksort is just make sure the leftmost element is your pivot. And of course, any element can be your pivot, but make sure your leftmost element is chosen as your pivot. So I set I to go after index or after the pivot element, and J starts off at R. And every time an element at index I is less, we move I by 1. And after every time an element in J is larger than a pivot, we move J by 1. At some point, we're going to cross them over. Now, this part here, we moved I and J. I was larger than the pivot and J was less. We had to swap these two values to fix this issue because right here, I and J, neither of them can move anymore because it would violate that condition. So we swap these values in order to continue. At some point, once I and J crossed, we know that everything to the left of I was less than a pivot, so we can swap the J value with the pivot to now have the pivot be in its correct position. So once I and J crossed, we swap J with that pivot. So the pivot now will go over here 5 and 1, and 5 will now be in its correct position because since we partition the list where we arrange everything to the left to be smaller than the pivot and to the right to be larger, we know that 5 is not going to be in its correct final position. So now we have to continue with quicksort. So at this point, I'm going to first quicksort the left side, then the right side. So again, so for the left side of this list, we're going to just have the 1, the first element, be our pivot. I will be at this position, and then J will be right there. And we're going to now have these move, essentially. So every time I is less, we move. So here I can move because element at index at this position is 0, less than a pivot, so I moves. And then the J value, well, it can also move because it's larger than the pivot, so J moves as well. And in this situation, well, I can't move, but J can. So I remains fixed, J moves, and we see here once again we cross the pivot with element, or we cross I and J. So the same rule, we swap the index J with the pivot to now have this pivot value be in its correct final position. So now what's going to happen is we're going to have 0 would go over here. 1 will be in its correct final position now because once we swap the J with the pivot, we broke the list into two pieces, so we know 1 will never have to move at this point ever again. I'll worry about the rest of the list later. I'm going to first process this side. So right now, having 1 as our pivot, we broke the list into two pieces, one with the 0, one with 4 and 2. So we're going to first quicksort the left side, so it's going to be a 0, and it has only one element, so we can just mark it as sorted. Perfect. And now we're going to go ahead and now sort the right side, 4 and 2. So once again, this will be my L, this will be R. I'll pick the pivot again just to be 4. And then I will be the element after the pivot, and J will be the element at the very end. So now what happens is, well, again, I can move, but J can't, because the value 2 is less than a pivot, so I can move, J can't move. So that means at this point, well, the J and the I crossed. So even though I went beyond the bounds, that's okay. The J and I crossed. So now we broke the list into two pieces again, one of size 0 and one that's going to have one element. So we're going to swap the pivot with element J to now have 0, 1, 2, and then 4 was swapped. So 4 is now going to be in its correct final position. and then 5. So we broke the list into two pieces, one of size 0 to the right of 4, which it's sorted already, and one of size 1. So we're going to quick sort this list, and it's only one element, so we can very easily mark it as sorted. So now we can see that we have the left side all the way sorted from their original list. So let's go back up to the top of this. So the left side, so we first broke it into two pieces. This entire left side right there is now sorted. So now we have to just simply sort the right side. So we have to call quicksort on this side, and once we sort this, then this will join with this part of the list, which will make it one big sorted list. So now we're going to have to, again, I'm going to pick my pivot to be the leftmost element once again. That's my pivot, so actually I'll write this all out. And there's my I value, and there's my J value. So we're going to, again, sort of move this. So I contains 6, so I can move, and J can't move because J contains 10. But as long as one of these two indices can move, we'll keep this loop running. So I is going to keep on moving while J remains fixed. At some point, I is going to go beyond the bounds like that. So in this case, this is a very bad scenario for partition, but it still is going to work. It's just a bad scenario because it's really nice if both I and J move equally, but in this situation, J couldn't move, and unfortunately, I was able to constantly move, so it just kept on moving. We only swap the I and the J values only if I and J both can't move, but I was able to. So now we're able to successfully partition the list. So in this case, again, we swap the pivot with whatever is in index J, like that. So we're going to swap these. So we're going to have 10 over here, then 6, 8, 7, and 13 will be in its correct final position. I'll move this down a little bit. So now we broke the list into two pieces, one to the right of 13, which is empty, and one to the left of 13, which will contain the rest of the list. So right now, I'm going to do I'm going to sort of do something that you shouldn't do for the homework, which is I'm going to pick a different pivot other than what's in the leftmost element. So instead of 10, I'm going to now pick 8 as my pivot. So to do this, I'm going to swap the 10 and the 8. So put the 8 over here, 6, 10, 7, and 13. I only do this, I put the 8 to the leftmost position because when I do quicksort, I like it where the pivot is out of the way. It's not getting involved with the I and J counters moving. Just to make the code and make the whole, conceptually following this algorithm makes it a lot simpler. So I like to have the pivot to the leftmost position every time. I'll put R over here as well. So right now, I chose 8 as my pivot instead of 10. But for homework, of course, please always choose the leftmost element as your pivot, just so it's easier on the grader. So right now, my pivot is 8. So right now, J can't move, but I can in this situation. So I increments by 1. And now we have a case where both I and J can't move because I is larger, J is less. So we have to swap the values in these positions because we want them to be able to keep moving. So once they can't move, we have a deadlock like this. You want to go ahead and keep this going. So we're going to swap these two values. So I'll put the 8 over here, 8, 6. I'll swap the 7 and the 10. And then 13 went over there. It's still part of our sorted list. This will be my L, this will be R. That's my pivot. And then I was over here at this index, and J is at this index as well. So after we swap them, we want to, of course, move I by 1, and J moves over by 1 as well. I'll move this down so you can see that. After we swapped, we had to move the I and the J, and again, we crossed these two indices. So when that happens, we have to swap the pivot with whatever is in index J to put the pivot in its correct final position. So we broke the list into two pieces. So now what's going to happen is we're going to have 7, 6, 8 in its correct position now, 10, and 13. So now I'll go ahead and maybe I'll just copy this a little faster. I'm just going to just copy and paste this. I don't have to rewrite all of that. Save some time. Good enough. So we want to preserve these. This is our sorted list. So now after we partition around 8, we created 2 sorted sublists, 7 and 6, and add 10. You have to sort these 2 individually. So again, we'll have L and R over here. My pivot, I'll choose it to be 7. We'll have I and J set like this because I is always set to the right of the pivot, and J will always be at the rightmost position. So in this case over here, J can't move, but I can. So I moves, and again, we partition the list. So we're going to now swap the pivot with whatever is in index J to give us essentially 6, then 7, 8, 10, and 13. Now, I'll go ahead and I'll stop right here, but if you were to do this, you would first sort the 6, which is a size 1 array, so you're done. Then you would sort the 10, size 1 array, done. So this whole part sorted, so is the left side, so we have a successfully sorted array. So just to go a little faster here, so I'm trying to condense this into a shorter video, so just because of WebEx's thing, but it happens sometimes, so I guess if it happens in the future, I'll just have to record like this as well. But anyway, that's sort of the execution of quicksort. Now let's go over time complexity analysis. So in this situation, well, let's go over the 2 different cases for quicksort. Well, actually, it's really based on the pivots. So let's suppose we have our initial list like this. So we're going to have sort of a hypothetical list. We have this situation. Let's say we break the list in half every time. So we pick a pivot that's going to create a partition that's going to partition the list into 2 equal pieces. So if we do that, it's going to create the following picture. We'll have this, then this is going to be where a partition will go. It's not partition. The pivot will go. That's going to go into this portion right there. So we create these 2 lists. We had the blue part, which was where a pivot was, which will be sorted position, obviously, because after we run partition, we put the pivot into its final position. And now we have these 2 lists right there. So we'll call quicksort on each of them. So we're going to assume for right now, we're going to always break the list into 2 equal pieces. So the pivot will be chosen in such a way that's going to always create this result every single time. And of course over here, we'll partition that list above, and it creates 2 sublists again, and the little box in blue will be where the pivot was. The pivot is in its final position. And then what happens is, well, we'll keep on working on this. So eventually, we'll break it further down. So I'll just sort of speed this up a little bit. So each of these breaks in half each time, which I guess can happen with quicksort. It's not a guarantee, but this is one scenario. And of course, at the very end, each of these size 1 blocks will just be sorted arrays. So we have our final sorted product. So all we're doing is partitioning again, and we create these smaller and smaller lists until eventually we have these size 1 lists, and then we have one sorted array. So in this scenario, we picked a pivot every single time that was always going to break the list into 2 pieces. But no matter what we chose for our pivot, we always have an O of n runtime for partition. So let's go ahead and talk about let's see, why is it always O of n? Well, we have 2 scenarios for partition. So I'll go ahead and I'll put this here for right now. I'll just write this here quickly. So runtime for partition. I probably should have put this actually above. Maybe I'll go ahead and I'll sort of move this up actually. So I'm just make a little room here for this. Got a little too carried away. That's kind of the penalty for trying to go a little faster, I guess. To try to condense this, I'm going to move this down a little bit. So I first want to go over what's the runtime for partition before I do all of that. So first, what's the runtime for partition? Is really the key for quicksort. So let's go up here for a second. So in this worst case scenario, we had, let's say we wanted to partition this list right there, the 13, 6, 8, 7, and 10. In the worst case, J remained fixed and I moved all the way to J. So we have 1, 2, 3, 4, 5 elements. It would take about roughly 5 steps to partition. So when we have this really bad case scenario, if the list size is n, it will take O of n time to partition. Now, if let's say the very top level, where I and j met in the middle, then it would not take n time, but each index I and j moved n over 2 times, both. So in this case, it ran n over 2 steps if it met in the middle somewhere, which is still linear. So no matter what pivot we choose, it will take asymptotically linear time to have I and j cross, whether I has to keep moving all the way to the end while j remains fixed, or if I remains fixed and j moves all the way to the end, or if they meet in the middle, no matter what we do, it will be some asymptotic time that's linear will be the runtime. So partition takes linear no matter what pivot we choose. It's always O of n no matter what, just like with that merge operation. So here, at every level, we want to sort of add up, we want to condense, or we want to just sort of count the number of steps. So initially, at that topmost level, it's O of n time to partition. And at this level right there, we have these two lists. Each one will take linear time to partition, but if we collectively add up all the work done at that level, it's O of n. So very similar to merge sort so far. Same idea here. If we collectively add up all the steps done by partition of each individual block, we'll see that it's going to be overall O of n if we add all of these up. So same idea like with merge sort. So in this case, what's going to happen is, well, just like with merge sort, we divide the list in half every single time. So we're going to have log base 2n number of levels, and each level takes O of n time to compute. So we're going to do O of n work log 2n number of times. So the runtime in this situation is O of n log n. And we'll go back up here in a second to analyze further as to how this actually works. But anyway, that's the runtime here. But this is actually a fairly good case scenario. This is where, okay, we were able to break it in half nicely every single time. But what if we don't break it in half every single time? So look at the example above. Let's take a look right here. In this case, the pivot was chosen such in a way that we broke the list in half. But in this example right here, we had 13, 6, 8, 7, 10. We broke the list very unevenly. We broke the list into sort of two pieces, one of size 0, then the pivot in its correct position, and then the rest of the list minus 1. So we didn't break it very nicely. So what if we have this scenario happening every single time, which definitely appears to be a very bad case scenario. Let me scroll down here. Let me just sort of draw the example for this. Let's suppose we do the same exact work, but this time we do a partition. We break the list in this sort of way. We have the pivot in its correct final position, and then we have the rest of this list. So we have this situation where we break it very unevenly. Then we have to call quicksort on that smaller list, which the result will be, well, it's going to just, again, partition the list very unevenly. We have our pivot in its correct position, and the rest of the elements are going to just be, well, they're not sorted. But we broke the list in this kind of fashion every single time. So imagine if we always have a case where a pivot is chosen in such a way that either the I remains fixed and j goes all the way to the I, or vice versa, then it's going to break the list very unevenly. Like this. So we're having this situation every single time. So we're breaking the list like this, and eventually at some point, as we keep on moving downwards, we end up getting every element is sorted. It'll sort it as well. It's going to still work. It's just that it's going to take possibly more time in this situation. I'm sort of blocking the way, so I'll move this down. So that's sort of an alternative situation with quicksort. So the pivot was very bad. So in this case, we broke the list very unevenly. So this happens, well, same idea as before. It will take O of n time because each of these lists, we have to partition every single time. So O of n over here, O of n here, O of n here, and so forth. So same idea, we're doing O of n work either way, but we have to do this actually n number of times this time, not log n time, because every level, we're going to have one list of size 0, and then the pivot in a sorted position, and then one list of size n minus 1, and then we partition that, and so forth. So this will actually model Gauss's formula, but if you want to guesstimate this, we're going to do this partition n number of times. So we're going to have n levels here. Each level takes O of n time, so we have n squared runtime. This is going to actually be, so let me go ahead and sort of move up for a second. So this is a two scenarios. You have O of n squared and we have O of n log n for quicksort. So the question is, well, what's the runtime for quicksort then? Well, we have to consider the worst case scenario and think, well, O of n squared is a runtime for quicksort because the worst case can happen. So quicksort is O of n squared, not O of n log n. Now let's go ahead and do a little further analysis on this portion. So, okay, this situation is n log n because in this scenario, the pivot chosen was the median. So if the median was chosen, it's going to actually run it in n log n time because we'll break the list in half every single time. Now, also, to make quicksort run n log n, we actually could pick a pivot that's not quite the median. If let's say it breaks the list in such a way where we have maybe 1/3 of the list on one side and 2/3 on the other side, that will still relatively be O of n log n. It will be a constant factor times worse than the median, but it will still be asymptotically n log n. So you don't have to break it always in the middle, although breaking in the middle would be the best case scenario. If you break in such a way where we have, you know, even like 1/5 on one side and 4/5 on the other side, that'll also be pretty good. As long as it's not just a small constant on one side, other side has almost everything, like we had in the previous example below. So that's if the median was chosen. We get n log n. But in this case, if let's say the min or max element is the pivot, then we have this situation, n squared, because we break the list very unevenly in this situation. So that's sort of the idea. So if we have a good pivot, we get a good runtime. A bad pivot, we'll get a bad runtime, n squared. So doesn't matter what the pivot is, it'll still work. It's just that the pivot decides the runtime for quicksort. So now the idea here is that this is actually the worst case scenario. And for n log n, that's your best case scenario. It's sort of the best and average case. So quicksort is very strange because, well, if you think about it, the probability of always picking the worst possible pivot is not very likely. So it's unlikely to have the n squared runtime. So quicksort, even though it is O of n squared, it's unofficially sort of treated as n log n because really that worst case is very rare. It's unlikely that to have happened, but because it can happen, we have to, you know, still say it's O of n squared. But for the average situation and the best case, it'll be n log n, but in the absolute worst case, it'll be n squared. So we kind of treat quicksort really unofficially as n log n, but worst case n squared. So if I tell you on an exam what's the worst case or what's the runtime for quicksort, if I just say just like that, you have to assume worst case, so O of n squared. If I just tell you, well, what's the average scenario for quicksort's runtime, or what's the typical situation, typical runtime for quicksort, well then it would be n log n. Now, it's also treated as n log n because it's very easy to avoid that worst case scenario. So let's go over, let's go over one last little topic here. So I want to go over the total runtime for partition. So I want to sort of summarize the partition. Oops, I'm trying to spell this correctly. Partition runtime. Well, overall, there's really two steps for partition. We first have to choose a pivot. Up to this point, this would take O of 1 time, or a constant time, because it takes, you just pick a pivot, done. Easy as that. And then that partition loop, well, that's going to take O of n time no matter what pivot we choose. So overall, O of 1 plus O of n will take sort of O of n time. So what we want to do is, well, what if we could actually always choose the median? So what ways can we actually guarantee a median? Well, we could, of course, can sort the array and then pick the n over 2 element, and we are guaranteed to have our median. But doing that, though, well, that defeats the whole purpose of doing this whole work. I mean, we're trying to sort the array, so if we sort it inside the partition phase, well, then there's no point to continue. And also, sorting takes kind of a long time, or it might take more than n time. Now, we'll prove later on what's the runtime for sorting, or what's sort of the lower bound for sorting, but we can't really prove that just yet. But anyway, what if we could actually find the median of an unsorted list in O of n time? So if you could do that, then instead of having this picking a pivot take O of 1 time, this will take actually O of n time to find your pivot. So O of n to find your pivot plus O of n to partition a loop. Overall, it's going to be O of n. It's going to be 2n, which is still O of n. So if there was an algorithm that could find the median of an unsorted array in O of n time, then we can always find the median quickly and choose that for your pivot, and then we'll always get n log n every single time. So there's actually an algorithm that does this. It's known as the selection algorithm. And I did link the book on Discord for the CS302 class that goes over this algorithm in that book. But anyway, this selection algorithm is going to find the kth largest element in the list. So if we set k to be n over 2, it'll find n over second largest element, which is the median element. So there's an algorithm that can find the median in O of n time, and we'll run that first, which means we're going to have O of n time actually to find your pivot. And then that plus O of n to the partition loop will keep this partition runtime still linear, but then we have a guarantee to break the list equally in half. So if you use this method, we are guaranteed n log n. So that's kind of why quicksort is really unofficially thought of as n log n, because it's so easy to avoid the n squared runtime. So that's the idea. So still, it's worst case O of n squared, but there are ways to avoid it, and it's unlikely to have that O of n squared runtime. So that's my talk on quicksort. So at least I got that part done from the video. And I believe in my class today, I also went over threading a little bit. So let's go ahead and just go into threading now. So what's a thread? Well, a thread is sort of a lightweight process, like a small, independently program that can run in parallel. So the best way to think of threading is think of Rick and Morty, Mr. Meeseeks. So Mr. Meeseeks, what is it? So if you ever watch Rick and Morty, which if you just watch that clip if you have time. So it's Mr. Meeseeks, so it's Meeseeks. So Meeseeks. It's really weird spelling. I think that's how it's spelled. So anyway, Basically, in that episode of Rick and Morty, what happens is they have a meeseeks box where you push the box and a meeseeks character pops up and he has to introduce himself as, "Hi, I'm Mr. Meeseeks, look at me." You give him a job to do, he'll do that job and then he poofs away. And of course, you can spawn multiple meeseeks boxes to have multiple jobs being done in parallel. So you can have one meeseeks box help Summer become this class president. One meeseeks can help Beth become a more complete woman, and one meeseeks box, which is the hardest one of all, to help Jerry improve his golf game. So you have three sort of meeseeks at one time doing a task, but doing it in parallel with each other. So you have to have one meeseeks wait for the one to finish. They can all do it at the same time. That's really what a thread is all about, really. So let's go ahead and write some code to try to understand how threads work. So I'll open up my terminal. I'm going to move into the desktop. So cd.dot. So I have my terminal in my desktop. I'm going to create a file. I'm going to call this maybe just thread01.cpp. The file should be right there. There it is. Perfect. So in order to write thread code, we first have to, of course, have our include IO stream. We have to include thread in order to use a thread type. And of course, using names space std int main. And of course, return 0 is very important, or else code grade is going to mark it wrong if you don't have return 0 in your code. So make sure you have that as well. And now, for a thread, well, just like with Mr. Meeseeks, we have to give a thread a job. So we're going to create a function. I'll call it void foo, a very creative function name. And I'm going to, of course, I'll just have it pass in the string. So I'm going to just include string just to be safe. So foo string. That's our function prototype. And this function will simply just output a message to the screen. Nothing really fancy. So void foo string msg, I'm going to call it. And it will simply see out msg followed by a new line. And of course, I'll put return here. You don't have to put that for void functions, but I guess I like to put those there anyway. So now what's going to happen is, well, we want to spawn a thread. Because of course I can call a function in main, just call foo, pass in a string, and we're done. But we want to actually have threads run this instead. So a thread type is just thread, and I'll say t. So right now, a thread is a variable t of type thread. It's an object of type thread. So we have to we have to call a constructor on this object t. So a constructor is going to actually create and spawn a thread. So for every thread function, every thread constructor, we have to pass in a few things. We first pass in the function, and in C++11 we can pass in function pointers. So we're going to pass in the function foo. That's the function we want to assign to the thread. And the parameter we're going to give to this foo is going to be, well, hello world. Of course, a new topic is covered right now, and we have to have hello world be our first message we're going to have the thread output. So right now, when I say thread t, I'm creating a thread variable, and it's calling a constructor, and the constructor requires a few things. It requires the function that you're assigning to it. So it's kind of like, here's our thread t. It's Mr. Meeseeks. It asks for a task. Okay, Mr. Meeseeks, go ahead and call a function foo, and I'm going to pass in hello world to this function. That's the string. So go ahead and output hello world. So it's going to take in the function foo and the string hello world. So we have this as a parameter. So let's say if foo had more parameters, for example. Let's say if I had it where I had an int over here. I have, let's say, int x. Then I'd have to also pass in another integer, another parameter by just saying comma 10. So in this case here, I'm creating this thread, t. I'm passing in a function foo. And the first argument will be hello world, and the second argument will be 10. If you want to have more than one parameter being passed in. But right now, let's have one parameter just to make things simpler. Just like that. And of course, you want to always join your threads after you spawn them. I'm gonna talk about what this actually means. So join really means that we're going to wait for this thread to finish before we move on, because we want to make sure we sync ourselves with the thread to make sure that we actually know it's done first. Because unlike threads, so with a function in C++, when a function terminates, it goes back to the previous calling function. With threads, though, it's not the case. A thread just goes and runs off, it will stop, and then it doesn't return back necessarily, because what's going to happen is int main and the thread t running the function foo are happening simultaneously. So there's no knowing when main will finish and when the thread will finish. So we want to make sure we always just allow ourselves to wait for the thread to finish first before we end our program and move on with our code. We want to make sure we wait for it to finish. So we have to have a join there. So I'm going to say the following. So to compile this code, g++-pthread. You have to include that pthread flag in order for it to compile. Now, if using an older version of Linux or a Mac, you have to also have std equals c++11. But most modern Linux systems already has C11 already used by default, so you don't have to include that, but -pthread has to be used. But on a Mac, however, on Mac terminal, you only have to use, you have to include this, but you don't have to include pthread. A Linux-based system, you have to include pthread. And then you don't have to include this because I think most Linux systems now automatically use C++11. So anyway, now we have that set up. Now let's go ahead and put our file here to compile. And it compiles. If I run this thing, outputs hello world. Nothing too fancy going on over there. So let's go ahead and spawn 2 threads this time instead of 1 and see what happens here. So I'm going to create thread T1 and thread T2. I'm going to have thread T2 also called function foo. So I'm going to assign the function foo to thread 2 as well. And for this thread, I'm going to assign it bonjour le monde, which is the French equivalent to hello world. And I'm going to say t1.join and then t2.join. Let's see what happens this time. So now what happens is the following. I hit the meseeks box and I spawn thread T1. I give it the job, the function foo with the parameter hello world. Then that thread goes and runs off and does its own work. Then I'll spawn another thread T2. I pass in foo, the same function foo, and I pass in bonjour le monde into this function as well. And then what happens is, well, T2 runs off. And T1 and T2 run at different speeds. There's no guarantee which one will finish first. They're both just going to go ahead and run. That's it. And then we're going to wait for T1 and T2 to stop before we end our program into main. We want to always sync our threads, make sure we have a barrier that we know, okay, at this point in our code, after T2.join, we know that T1 and T2 both had to have stopped. So T1.join will sit there and wait until T1's done. Once T1's done, okay, then we're going to sit here and wait for T2. Once T2 is done, we move on. Let's go ahead and compile this code. If I run this, oh, that looked actually nice. Output hello world. Let's run this again. Now I kind of output in a very weird way. Output hello world and then bonjour le monde right away on that one line. I guess I can't get it to output all different ways. I guess that's okay for right now. But anyway, what happened was this. The reason why we had this very bizarre output was because thread T1 was writing hello world. And before it was able to actually finish, remember it first had to output a new line. Before it could do it though, thread T2 got a hold of cout and it started writing to the output. So think of it as like 2 Mr. Meeseeks boxes, or 2 Mr. Meeseeks characters, sorry. And they're basically both trying to write to the same piece of paper. So one Mr. Meeseeks will write, and then the other Mr. Meeseeks will grab him and throw him away, or kick him off, and then he'll start writing, and the other Meeseeks comes back and kicks that Meeseeks off, and he'll write. So imagine having one piece of paper, and they're both trying to write on there. What kind of chaos can possibly happen? Well, that's what's happening right now with these 2 threads. So thread T1, T2 are both trying to write at the same time, and there's no knowing what will happen. I mean, in theory, what could happen is we could actually end up getting an output where it could be HE, and then we can have BONJ and so forth. So this could be all kinds of weird sort of conglomerate output. Now, luckily, it ended up being kind of nice, but there's no guarantee it came out this nice. It could have been all over the place. There'll be examples we'll do probably next time that will sort of, have more crazier output. But anyway, that's the case right there. Now, of course, if I were to not join these two threads, then our program will have a runtime error. So if you see a runtime error like this, it means maybe your threads weren't really joined properly. So here we have this aborted. Because what happened right now is thread T1 was writing, then thread T2 was writing, but neither thread was done yet. But int main finished before the two threads could have stopped. And that's going to be a problem. So these two threads are running away, and we didn't really confirm. Now, luckily, they both did stop, because T1 and T2 will stop, luckily. But the problem here is we don't really know if it stopped for sure. So the program sort of didn't like that. So, of course, you want to always make sure you wait for your threads to stop once you spawn them, or else you have that error. So now, to fix this problem, so for example here, with these threads, well, they're both outputting cout at the same time. So one way to sort of fix this problem, so we don't have multiple threads at the same time writing to the output, we have to include this mutex lock over here. So mutex type, I'm going to create a variable called mutex and call it tlock, like this. And what I'm going to do right now, I'm going to wrap a locking expression around this code. So tlock.lock. So I'm going to make this tlock variable global because I want to have every thread share this one variable tlock. And tlock.unlock. Like that. So in this situation, what's going to happen now is only one thread will be able to sort of lock. So think of this lock as like a door to the doctor's office or something. So what happens is only one person can enter a doctor's private room at a time. So one thread calls tlock.lock. It enters this part of the code in between those two lines that lock and unlock. Only one thread can be there at one time. The other threads are kind of waiting for the door to be unlocked so they can get in. So what happens over here is one thread gets in, outputs the message, other threads sort of waiting there, can't do anything, and then once we unlock, this foo function is done, so thread T1 is finished at that point with its output, and then thread T2 now will be able to make its output. Or if I say T2 first locked, then T1 will be sort of left out, basically. So that's sort of the idea with mutex. So there's certain parts of your code you want to make sure you can't have multiple threads at the same time running. Now, of course, you don't want to have your entire function be under a tlock and unlock. If you do that, then there's no purpose of having threads. So there's certain parts of your code that threads can do in parallel, but there's certain parts that it can't do in parallel because they'll cause some type of an issue. It's actually a race condition problem, which you'll learn about that more in your operating systems class. So there are moments where you have to lock and unlock to avoid having any kind of problems with your threads. But in general, you want to have most of your thread function code not be under mutex lock because you want to have threads do stuff in parallel. So think of like this. So we'll do an example next week on this. But think of, let's say we assign both Mr. Meeseekses. We assign one to do some crazy calculation, and other one also will assign some calculation to them. And once they're done, they're going to write their output. So we can have the two Meeseekses do their own calculation independently of each other. And once they're ready to write, only one of them can write at a time. So we're going to sort of do work on that next time. But I think this sums up the class from today. So I'll continue on this and recap a little bit of this next week. So until then, take care and sort of stay safe and have an awesome rest of your day.